I will begin with a word of prayer. Heavenly Father, we thank you for this day again. I thank you for these students and just ask that you'd guide our steps today, help us to glorify you we do, and just to understand a little bit more about integration today, Lord. In your name I pray, Lord Jesus. Amen. So I hope you enjoyed your day off, sort of. Not really. I hope you enjoyed it more than I enjoyed parking today. But, let's see here. So, we need to talk about how we deal with integrals over regions in space, which maybe are not quite as simple as we've talked about before. So we're talking about integration over, volumes in 3 dimensions for the most part. And so the story basically is the same as what we've done up to this point. The big difference, of course, is like now we have to talk about how do you integrate over a volume where it's not so nice. All right, so like here, this volume, for instance, we could talk about x, y, z such that, let's say 0 is less than or equal to x, there's less than or equal to 1, 1 less than or equal to y, less than or equal to 2, and x plus y less than or equal to z, which is less than or equal to, let's say 10 plus x squared plus y squared. All right? So if this is the volume that you're talking about, all right, this particular region, how would we set up a triple integral over this thing? And so, I can kind of picture it roughly, right? I don't even need the picture because of the way I've described the region, but let me just try to picture it. So we're like x is going from 0 to 1, y is going from 1 to 2, right? So we've got like that, basically here's 0, 1, in the x direction. And, my bad, let me put it over here. Here's y. So it's over here, right? So it's like, that's just the, where x and y range is over, right? But z is stuck between x plus y, which is, all right, so z equals x plus y is a plane, right? And if you look at that plane, when x is equal to 0, you got y equals to z. So it's something like this here, and, oh man. Oh well, I think I know what's happening here. And if I put x equals to 1, which is here, I get 1 plus y equals to z, which is to say I get, something like, I can't draw it worth anything, but it's something like this. Oh man, I can't draw this worth anything. But there's some kind of shape down. Let me just be very sketchy here. So this would be z equals to x plus y. And this 10 plus x squared plus y squared, it's got a, it's got a z-intercept here of like 10, right? And it's like a bowl that goes upward. So it's something like, I can't even draw it, but there's something at a top up here, right? And between this up here, which I'm foolishly trying to graph as 10 plus x squared plus y squared, right? There's a top. And any point that I pick between this plane, right? Between this plane and between this paraboloid, right? Between the plane and the paraboloid, we find our volume. So a typical point in here, x, y, z, all right, a typical point in there is what we're up against. But I've already given it to you explicitly here. So the x is between 0 and, my bad, the x equals to 0, x equals to 1, this is y equals to 2, this is x, my bad, y equals to 1. So like every point in this volume that we're trying to understand the integral over, it's subject to these three conditions, right? X is between 0 and 1, y is between 1 and 2, and z is between a plane and a paraboloid. It doesn't really matter that we can't draw the picture at all. We can set up the integral, all right? And so the way that goes is like this. The integral, well, the triple integral, over the volume of a function of three variables, perhaps, x, y, z, dv, is equal to, well, the integral from 0 to 1, the integral from 1 to 2, the integral, okay, so the lower z is x plus y, the upper z is 10 plus x squared plus y squared, and then I have to have f of x, y, z times what? I got to vote for dz, then dy, and then dx. Very good. So if I don't know, the picture is very sketchy, right? But the projection of this volume down onto the xy plane should just be that square, right, that I've pictured there. But the lower, the lower edge of it, the lower surface of it is a plane. The upper surface is like some sort of subset of the paraboloid, which is like an, upward opening bowl. Anyway, so that's how we would set up the integral. Can you tell me one other way we could set up the integral here? Like there's another one that's easy. We could also set it up this way, right? Integral from 1 to 2, integral from 0 to 1, integral from x plus y to 10 plus x squared plus y squared, f of x, y, z, right? Now we've got dz, dx, dy, right? We could do that as well. I'm kind of scared of trying to do the other. I mean, in principle, there's 4 other ways to set up the integral. All right? But because I can't draw a very good picture for the others, I think I'm going to just stop this example here. But this is, it's pretty easy to set up the integral if we're already given an inequality which describes the integration in question. Like here's another example. You're given that the triple integral over a volume of f dv is equal to the integral from minus 1 to 1, the integral from, let's say, the square root of 1 minus y squared to the square root, there's a minus out here, to the square root of 1 minus y squared, and then integrating from minus the square root of 1 minus x squared minus y squared to the square root of 1 minus x squared minus y squared, f of x, y, z, d, z, d, x, I guess, dy. So my question then for this one is, can you work backwards? Can you tell me what the volume is that we're formulating the integral over here? Like, when I write these bounds, right, what does this tell me about a typical point in V? This means that if we pick x, y, z, in the volume that we're integrating over, it has what? It has 3 things. Number 1, the easy thing, minus 1 less than or equal to y, less than or equal to 1, right? We got that. From the middle bound, we've got what? Right? We have that. And the inner bound tells me that 3 minus the square root of 1 minus x squared minus y squared is less than or equal to z is less than or equal to the square root of 1 minus x squared minus y squared, right? So we can unwrap this mystery, right? We can figure out what this mystery volume is by trying to piece together this information. All right? Like, I wasn't very, like my first example, I mean, you could call this z base, z top, right? Like the top z and the bottom z are pretty more or less clearly defined in that problem. And here, well, here you go. This is the bottom, the base z, right? And here's the top z. Apparently it's a volume which has a well-defined top and bottom in the z sense, right? Not every volume's like that. Yeah? But this one is. And so, like, we can, let's we've got z is either plus or minus the square root of 1 minus x squared minus y squared, right? So can we understand what that is? Square both sides, right? We get what? Z squared is 1 minus x squared minus y squared. Lo and behold, x squared plus y squared plus z squared is equal to 1. Well, this is the equation of the unit sphere, right? It's the equation of the unit sphere, and that pretty much unlocks what we're looking at here, you see, because, we've got the top, right? Z top equals to the square root of 1 minus x squared minus y squared. And then we've got, down here, z base is equal to minus the square root of 1 minus x squared minus y squared, right? And where do they meet? I mean, this one is kind of interesting in the sense that, like, my example 1, there's sides, right? There's part of the example 1, you've got x equals to 1, or y equals to 1, or x equal to 0, y equals to 2 as sides on that. Is there a question? Okay, so right here they meet at the equatorial circle, I think, right? Actually, what is this? It's a circle, yeah. Isn't it number 2? Like from number 2, if we look at the equals case, we've got x is equal to plus or minus the square root of 1 minus y squared. Square that, and we get x squared is 1 minus y squared. So we get x squared plus y squared is equal to 1. Right? That's this right here. But that's also, this circle. So in particular, depends on what I mean by my picture. Well, I guess I'll foolishly put z like here, and I'll put x this way, and I'll put y that way, right? So if you want me to, I can graph the plus square root is over here, right? That's x is equal to the square root of 1 minus y squared, right? And then on the back half there, yeah.
But if you set, can you do the same thing for y and set x from -1 to 1? Is that allowed?
One thing at a time, but yes. Okay. And here we have x is equal to minus the square root of 1 minus y squared. There are other flavor options, but we'll finish eating this pizza before we put the toppings on in another order. So here, yes. So this is the back y. This is the front y, right? And then, of course, y goes from -1 to 1. Oh man, I did it. Really? This is stupid. My picture is wrong. What do x is positive for the, right? I wanted to say the back y is this. This is the back y, right? The front one, though, it goes in my picture like that, right? And to make sense of it, I should show you that the y-axis continues like that, all right? And then, of course, number 1, well, y ranges from where to where? From here, right? Y equals -1 over to here, which is y equals to 1. Now, we didn't need to do all of this to understand that the answer to the question I posed is clearly that v is what? V is the unit ball. So we could say, well, v could be described like this. X, y, z, such that x squared plus y squared plus z squared is less than or equal to 1. Right? That was the answer to the question. And I think that was already apparent once we even just examined 3. Right? Once you know that the upper hemisphere is the boundary for z, and the lower hemisphere is the other boundary for z, I guess the question is, does 1 and 2 actually impose any additional conditions? Right? Yeah, question?
You said my question.
Oh, good. But look, there's another way to look at this, which is kind of as a project of carving. This is a 3-step sculpting process. Carving the sphere. 3 steps of carving the sphere. Now this is a little bit silly because this process I'm about to describe to you, it begins with an infinite slab of cheese. So you have to imagine all of our 3 filled with cheese. You could use something else if you prefer. I mean, if you want a very firm jello would also suffice. All right? But this setup that we just talked about, number 1, -1 less than or equal to y less than or equal to 1. I can picture that. What's going on here is if I draw, foolishly, attempt to picture x, y, and z, what is y equals -1 and 1? Vertical lines is kind of the right idea, but they're what? They're actually, they're not lines though. They're planes, right? They're planes, infinite planes. They go up and up, right? So, oopsie. So my point is, we carve out that infinite slab, right? So our initial cut leaves us with this, I can't draw it worth anything. It leaves us with this infinite slab like this, right? Y equals 1, and back here, y equals -1, right? And it goes on and on. Step number 1. Step number 2. We appreciate the import of item number 2, which is minus the square root of 1 minus y squared less than or equal to x less than or equal to the square root of 1 minus y squared, right? What are these? You notice that these are cylinders. They're half cylinders is what they are. So what then we're doing is we're taking this slab, right? And I'm gonna illustrate this cut in red, and we're cutting out like this. Right? So there's my y equals minus the square root of 1 minus y, listen to me, x equals to 1 minus the square root, and in the front, x equals 2 plus the square root of 1 minus y squared, right? And so what that leaves me with is actually a cylinder, like you said, right? But it's an infinite cylinder with a z-axis in the top, right? Here's my x, here's my y, whatever. And then step number 3, right, is what? Yeah, step number 3 is to impose the third condition, which was that, minus the square root of 1 minus x squared minus y squared less than or equal to z less than or equal to the square root of 1 minus x squared minus y squared. All right, so that takes this and it whoop, whoop, and we're just left with the sphere, which is the actual volume. This is the thought process. Now, it just so happens that it seems like the answer is given by the last step, but that's just a quirk of this example. You see, if I change the problem a little bit, like suppose example 3, that instead I give you, say, integral from 0 to 1, integral from 0 to the square root of 1 minus y squared, and then integral from 0, or not say from 0, let's say from 1 to the square root of 1 minus x squared minus y squared. dz, dx, dy, right? If I did that, how would this carving process change? Like, let's think through it.
Would it be like a quarter of a sphere?
Well, I mean, it's not even that. So first of all, we have half of the slab that we start with, right? Because we only go, basically, we start with, just the slab that goes from 0 to 1, right? And then the next thing is what's my next cut? You don't mind, I'm going to do it all in one picture. My next cut is I put x starts at 0, right? And it goes out to what? X equals to the square root of 1 minus y squared. You see that's this half cylinder, actually. So what I'm left with, if I just look at these two, what that describes for me is this, I can't draw down here worth anything. It describes for me, like this infinite half cylinder, right? But then z is ranging from what? I can do this integral. Do you know what the answer is? The answer is 0. Very good. Yes. Because if you look at z equals to 1, and the equation for the top of the sphere, right? They intersect right here. So this is very, very dumb. The volume that's described by the inequalities implicit within this triple integral just leave you a single point. Ooh.
What if you do from 0?
I hadn't thought of this problem before. Yes?
What if you do from 0 to...
Yeah, let's make it more interesting. Instead of 1, let's make this a half. All right, and then all of a sudden we have something to do. So, so I can't draw worth anything. So then, I guess I probably have the best chance of drawing it on top of a sphere. So it's like above the halfway point, right? And it's just on the front half of the sphere, if you will. It's like this. If I draw it from the side, it looks kind of like this. Still not quite right. So here's the z, here's the x, y is coming out at you. So the volume's like this thing. All right. So I have front-loaded this discussion with, I think, like pretty challenging examples. Let's try to do one that's a little bit easier, yeah? So suppose we have a volume, and this is a standard example. This is a good example for us to work. Example 4. Let V be bounded by the coordinate planes and let us say x plus 2y plus 3z equal to, I'll make it 6. All right. Given that 1, 1, 1 is an element of V, find the integral over this volume of, let us say, x dv. So I'll make the function we're integrating relatively benign. It's just x. All right? So what is putting that point? Can you guys visualize what's going on here before I even draw any pictures? Like, what is telling you the point 1, 1, 1 is in the volume mean about this space we're trying to integrate over? It should show to you that the volume we have in mind is in the first octant, right? It's where x, y, and z are all positive. So like, basically we can visualize the edges of this volume as like the coordinate planes, the xy plane, the xz plane, the yz plane, and then the other edge to the volume is just the plane which is given, x plus 2y plus 3z, right? And I think we can draw a decent picture of this one, unlike my first example. Yeah? So, all right. This is not necessarily to scale, but there should be plenty of room here for us to organize our thoughts. Because basically the issue is we need to come to terms with the different points in here. Like, first of all, let's figure out what these 3 points are. Those are going to be mission critical for sure. How do you find those points? Set each one equal to 0. Which is the one in the each in your statement? Like, let's be specific. Oh, dudes. Why? Goodness. Whoa. Maybe I should stop now. That's very disturbing. All right. Anyway. Okay. So here, this point has what? X, well not x, but everything else. Y equals to z equals to 0. So x is equal to what? 6 apparently, right? So this point is 6, 0, 0. How about up here? This point is what? There we have x equals to 0, y equals to 0, so z equals to? Z equals to, so this tells me that 3z is equal to 6, therefore z is equal to 2. It's important for us to understand where that 2 you guys are pulling out of the thin air come from. It's because of the plane equation, right? So very good. You're right. Now this point right here has what? This has x equals to 0 and z equals to 0. And when I plug that data into the plane equation, I get 2y is equal to 6. Therefore, y is equal to 3. So this point is 0, 3, 0. Right? Okay, so let me tell you something that's true, but not actually helpful. And this is something that we all struggle with, because we'll find something that's true and say, well, that's true, that must be it, right? So how about this? 0 less than or equal to x less than or equal to 6. True? Great, true. 0 less than or equal to y less than or equal to what? 3, right. 0 less than or equal to z less than or equal to 2, apparently, yeah. Exactly, that would be a box. If I just impose these 3 conditions, that does not capture this. That captures this thing, right? It just gives me that box-like region, right? And that's not the question that we're faced with. We're faced with integrating over this, like, tetrahedron, irregular tetrahedron. Yeah.
For the box, wouldn't it be x equals 6?
Oh, yeah. Thank you. I felt like something's wrong. Thank you. So that's not what we're doing. Now, if we think about the cheese, right, we could begin the process of slicing this shape out of 3 dimensions with any one of these cuts, right? But what happens after that is different. So we need to commit to one of these. I personally kind of like to commit to the which is going to be nicest? I don't know. Maybe the Z one. Do that one first. No, let me do. Let's do X first. Yeah, fine. It doesn't matter. So we'll stick with this. We're gonna make that one of our inequalities. All right. So that's the first thing. Now this guy right here. What's this? This has z equals to 0, right? And it also has x plus 2y plus 3z equals to 6. So actually, this guy right here is x plus 2y is equal to 6, right? That is what this is. And that's a plane. It's an infinite vertical plane, right? So if you start by slicing from 0 to 6, then you slice off from 0 to whatever this is, then you've got like a giant triangular prism. So let's make this a little bit more specific. This is y is equal to what? 3 minus 1/2 x, right? So if you take any point in here, let's say x, y, z, I need to be able to write down inequalities which are true for that. So we all agree 0 less than x less than 6. We're all fine with that, right? I think we should also be able to agree that 0 is less than or equal to y is less than or equal to 3 minus 1/2 x. See that? That's because this right here, if you continue up or down, we've got an infinite vertical plane, and clearly the tetrahedron is on the back side of that with respect to y, right? It's this. If I think about this point right here, if I go here, I get this point out, right? If I go here to here, there's some point. And if I go from here to here, the y, right there, x, y, z, right? That point, in terms of y, is between 0 and 3 minus 1/2 x. It's always between 0 and, the point 3 minus 1/2 x for y, which is on the top plane. All right, let me stop talking. So then, how about z? Well, z is kind of easier in this problem because what's the z bound? we have 0 less than or equal to z less than or equal to what? Like how do you define the top z here? Take this, right? It's governed by this equation, right? Man, this marker's trash. Oh well. So I do what? I do 6 minus x minus 2y all divided by 3, right? That's what I get if I solve that for z. All right. So the integral that we're after, we can finally do. We got everything we need to set it up. We're doing the x integral last. We're doing the y integral in the middle. The y integral was 0 to 3 minus 1/2 x. The z integral goes from 0 to, can you guys simplify that a little bit? That's what? That's z equals to what? Z top is 2 minus 1/3 x, right? Minus 2/3 y, right? Two minus 1/3 x minus 2/3 y, and then I've got to do x. All right, now here we go. dz, dy, dx. Right? No, I mean, this part just requires, at this point it's mechanical, right? But let's go through it. It's something we all need to learn. So integral from 0 to 6, integral from 0 to 3 minus 1/2 x. And then I've got 1/2 x squared, right? Evaluated from 0 up to 2 minus 1/3 x minus 2/3 y. Oh, wait a minute. Oh, thank you. That's a relief. So this should have just been what? xz. Yeah, thank you. Well, now I feel dumb. So this was equal to z, and this was equal to z, right? And that is followed by dy and then dx. All right. So I didn't really need to write all that, right? I could have just went straight to this step, and that would have been totally legitimate. So sorry for writing more than I needed to, but that is x times twice 2 minus 1/3 x minus 2/3 y, close parentheses, dy, dx. Right? So like that middle step, when you have your thinking clear, that step can be skipped. Now we need to integrate with respect to y, right? So I'm going to make one more step in here before I do that. Integral from 0 to 6, integral from 0 to 3 minus 1/2 x. All right, so there's two pieces here. The one piece is x times 2 minus 1/3 x, right? And then I've got minus 2/3 xy, right? dy, dx. So the way this works is we have the integral from 0 to 6, and then we're going to have x times 2 minus 1/3 x times 3 minus 1/2 x. Minus 1/3 x y squared evaluated from 0 to 3 minus 1/2 x. And that's all integrated over x. Now, I did a little trick right there. right? What did I do? Let's try to understand it. My point was this, you end up with x times 2 minus 1/3 x times y, evaluated from 0 to 3 minus 1/2 x, right? But what happens, just the first piece, right? What happens when you just have y times something integrated from 0 to the upper bound is you just end up multiplying by the upper bound, right? So that's why I wrote down what I wrote down up here. It's just this. Yeah. Now the other part I need to think through, because there I had to anti-differentiate y to 1/2 y squared. The 1/2 and the 2 cancels, leave me 1/3 xy squared. Right? Now let's continue. I'm going to do a little bit of algebra on the first piece. This is, anyway, fine. I'll leave the x out front actually. That's 6 minus x plus 1/6 x squared. And then over here I've got minus 1/3 x times 3 minus 1/2 x quantity squared. Close big parentheses dx. All right, integral from 0 to 6 of, apparently, 6x minus 2x squared minus 1/6 x cubed minus 1/3 x times, well, that's 9 minus x plus 1/4 x squared. I think. I could be wrong about that. Let's think through that. When I do the cross terms, I've got minus 3/2, which is, that's not a minus x in the middle, it's a minus 3x, I think. Because I get minus 3/2, which gives me a total of minus 3 x's in the middle. And then, of course, I get the 3 times 3, which is 9, and the minus 1/2 times minus 1/2, which is a quarter. One more step here, maybe 2. Integral from 0 to 6, 6x minus 2x squared minus 1/6 x cubed minus 3x. Oh, did I change my minus to a plus? That's not, I mean, other way around. Yeah, plus 1/6, thank you. So this is minus 3x, and then I get the 3 and the third cancel. Minus minus gives me plus, so plus x squared. And then minus 1/12 x cubed dx. One more step before I integrate, I think. How many x's do we have altogether? I'm not Taylor Swift. This is not a difficult question. Come on. I'm sorry, who's Taylor Swift? What? Oh, sorry. It's my favorite thing on Facebook is some post about Taylor Swift. I just put in the comments, who's Taylor Swift? And people start explaining it. It's great. It's great. Anyway. Sadly, I know. Let's see here. So, negative x squared. All right. What's 1/6 minus 1/12 is, 1/12. Okay, yeah, cool. So plus the 6th wins, right? 1/12 x cubed. All right, and lo and behold, we get ourselves 3/2 times 6 squared minus 1/3 times 6 to the power 3 plus 1/12. Oop, my bad. What's 4 times 12? 48. 1/48. 6 to the power 4, which equals, time for me to get my calculator. Let's see here. Oh no, I left my calculator in the office. Oh, wait a minute, no I didn't. Haha. Haha. All right, what we got? 36. 36 times a 3 divided by a 2. 54 is the first term. Minus 6 cubed divided by a 3. Nope, get back. Not that divides, this divides. All right, thank you. 3. That's minus 18 total, and then plus 6 to the power 4 divided by a 48. 9. 9 is the answer.
Wow.
That's cool. I just made this thing up, you know. All right. What if we tried to set this problem up differently? Any questions before I do something like that? All right, let's try to set this problem up differently. Instead of starting with 0 less than x less than 6, let us try, which one? Let's do the y. Maybe we should do the z. Z is weirder. Let's do z. Suppose you do that. So we're starting with an infinite horizontal slab, right? So I need somewhere to draw. All right, so we're going between 0 and 2 for z. I think it's still basically governed by this thing, right? Which is x plus 2y equals to 6 there, right? So if I'm going to do 0 less than or equal to z less than or equal to 2, then I got choices, but one of the choices I could do is 0 less than or equal to x less than or equal to what? Like the x is between here and here, right? So I've got x equal to 0 back here. I've got x equal to 6 minus 2y up in the front of the thing, right? So I can do 0 less than x less than 6 minus 2y. And then how about my y? Yeah, that's governed by the plane, right? So I got to solve that for y, and I get, 6 minus x minus 3z all divided by 2. So in other words, we could also have set up this problem. 9 is also equal to the integral from 0 to 2, the integral from 0 to 6 minus 2y, the integral from 0 to 6 minus x minus 3z all divided by 2 of x. Now I got to be careful. We do dy first. We do, dx second, and we do dz last. And I don't know, that might have been easier even to actually do that. I gravitate towards our first description as my usual way of doing things, but there are other ways. Anyway, we'll do more of this stuff tomorrow. So thanks, guys. What are you doing?